This lecture is going to continue our exploration of expectation of random variables, and then from expectation we'll introduce the concept of variance. So as a review of last time where we ended off, we had defined what expectation of a random variable was, and we said that if we have some random variable x, then the expected value, often called the mean, is defined as, and there are two cases. One, if we have a discrete random variable. In that case, the expected value of x, denoted e of x, is the sum over x, all possible x or x in the support, of x times little f of x, and this little f, of course, is the probability mass function. The second case is if we have a continuous random variable, and in this case we define the expected value of x as, so the sum, the integral over the whole real line of x times fx dx, and now in this case little f here is the pdf, the probability density function. We said that one way to interpret the expected value, of course the name gives part of it away, it's the value we expect to see, it's kind of a typical value, the average value. But you can think of it as if you have, say, maybe this is my pdf, and if I were to kind of imagine that, I have various densities of maybe some material, where would I put my fulcrum if I'm going to balance that? So you can interpret the expected value as the balancing point. That's supposed to read balancing. Let's try writing that one again. There we go, the balancing point. Let's look at some examples, because this is all a bit abstract. So today is going to be a lot of examples of how to calculate expectation. So you'll come out of today knowing how to do expected value. Okay. Example. Let x be a random variable, and we're going to say x is distributed with an exponential distribution with a parameter lambda. Okay, so this is the how we denote the exponential, what's called the exponential distribution. This lambda here is some positive parameter. So we read that as x is distributed as the exponential distribution with a positive, what's called the rate parameter, in this case, lambda. What that means, practically, that's all just notation, that means that my pdf, so this is going to be a continuous distribution. This means that my pdf has the following form. Lambda e to the negative lambda x for x positive. The implied part, which I didn't write, is that the pdf here, fx, is 0 when x is less than or equal to 0. And so what this looks like, if we draw a graph of my pdf, here's fx, here's x, this is maybe my 0 point. Let's make fx red. Okay. Below 0, fx is 0, and then it follows something that looks something like this. This is lambda e to the negative lambda x. And again, lambda is just some number, some positive number. So this is a very common continuous distribution. And a question that we might have is, what is the expectation or the expected value of x if it follows this distribution. So, of course, we know expected value of x has a formula. This is a continuous random variable. And so our formula says we integrate over the whole real line, negative infinity to infinity, of x, fx, dx. And in our case, so let me pause here and back up. Beyond this point, this is just a calculus problem. It's a calc maybe 2 problem. So the probability, kind of new probability content stops here. Beyond here is just calc 2. Nonetheless, let's go through it and we can show for an exponential random variable with a rate parameter lambda what the expected value is. In our case, we don't actually have to integrate over the whole real line because we know that fx is negative. 0 for negative values. So we can just look at the positive part. There's no contribution from the negative part. And so we get this integral to solve. And we can plug in, I suppose, for what fx is. It's lambda e to the negative lambda x dx. Now, this is a calc 2 problem, and this very well could show up on the final for a calc 2 class. How we're going to solve it. Let's remember our favorite tool, integration by parts. So integration by parts says that the integral of u dv is uv minus the integral of v du. And we can probably make our integral into this form if we carefully choose uv. So let's look at how we can do that. We could choose u to be x. That's nice because then du is just dx. And so the rest of our integrand must be dv. So dv would have to, in this case, be lambda e to the negative lambda x dx. And you can kind of solve that integral in your head to get back what v would be. And it's not so bad. It's e to the negative e to the negative lambda x, right? So if I differentiate that, I would get lambda e to the negative lambda x. Okay? So those are my choices. And indeed, according to my integration by parts formula, then integral, and let's leave the limits off for now. Let's just do the indefinite integral. The integral of x lambda e to the negative lambda x dx, that we could write as u dv, which of course is uv minus the integral of v du. uv is x, so negative e to the negative lambda x, and we got to subtract off the integral of v, which is e to the negative lambda x. Of course, there's another negative, so we can change that to a positive. And then du, very nicely, it's just dx. Okay. One little more step here. Got to solve this last indefinite integral. And how do we do that? Of course, that will give us what? Minus 1 over lambda e to the negative lambda x. So not so bad. A little integration by parts gets us there. Or of course, we left off our limits. So let's go back and put our limits on. Our original limits were from 0 to infinity. And of course, this has to be integrated from, or has to be evaluated at 0 infinity also. So this from 0 to infinity, my limits of my integral from 0 to infinity. And so if we're actually going to evaluate this now, right? So we have to evaluate this all according to our integration limits, right? That's how integration by parts works. So our first part here is x e to the negative lambda x, basically. And when x is 0, so it's going to be a difference of two things, a difference when it's infinity and difference when it's 0. When this is 0, of course, the whole thing is 0, right? It's 0 times something, 0, okay? What happens when this is infinity? What happens when I send x to infinity? Well, x goes to infinity, but e to the negative lambda x is going to go to 0. So x goes to infinity, e to the negative lambda x, lambda is positive, so this thing goes to 0. So if I multiply them, I'm going to get this indefinite 0 times infinity, right? There's not an easy limit. What we have to use is L'Hopital's rule, and you'll see that x e to the negative lambda x goes to 0. So I'm not going to do the details, but if you actually justify this with a Calc 1 argument, you would use L'Hopital's rule, and you could show that this whole thing goes to 0. So actually, very nicely, both parts go to 0. The intuition is that x goes to infinity, okay, but e to the negative lambda x goes to 0 really, really, really fast. And it goes much faster to 0 much faster than x goes to infinity. So it kind of dominates the expression. And so the whole expression is dominated by e to the negative lambda x, which goes to 0. So I would, on, say, a homework or exam, I would be satisfied with you saying, yeah, e to the negative lambda x dominates the expression, and therefore the whole thing goes to 0. You don't have to go through a L'Hopital's rule explicitly. And this works for any power. If I had, say, x to the 5th or the 7th or whatever, e to the negative lambda x is going to dominate any polynomial in x. Okay, so that's our first part. Of course, then we subtract off, and we have our second part here. And this one's much more straightforward, right? So at infinity, again, e to the negative lambda x goes to 0. That's nice. And at 0, e to the negative lambda x is 1, so I get minus 1 over lambda. All then left to us is the minus 1 over lambda is a 1 over lambda at the end of the day. So actually our integral, which looked pretty nasty, values to something really nice. And what we get is that if we have this exponential distribution, the expected value, which is what we were calculating here, is just 1 over lambda. So that's our first kind of real example of expected value. Basically, it's an integration problem, which is what kind of expected values for continuous random variables are. Let's look at some more examples. Now let's look at a discrete example. So let's look at a binomial distribution. So here's my notation. Again, BIN stands for the binomial distribution. And this is a discrete distribution. And I've denoted here, not written particularly well, but denoted here, that this thing has two parameters. An integer greater than 0 and a, let's call it a probability. P is some number between 0 and 1. The canonical experiment, as were, that you can think of. So most random variables have some kind of canonical experiment. You can think of them, right? Random variables are supposed to be kind of summarizing some outcome of some random experiment. So they all have some kind of canonical experiment that you can think of the random variable as being a realization of, whether or not it actually is. And the canonical experiment for a binomial random variable would be if I flip, that's not how you spell that, if I flip a coin n, so here's my parameter n, this integer, n times, and, well, let's say n times independently, and the probability of getting a heads on any flip is some p, some probability between 0 and 1, then x, and if I let x be the number of heads among my n flips, then x has a binomial distribution with parameters n, the number of trials, and p, the probability of getting the heads. You could think of it instead as a 0-1 experiment, any kind of binary experiment like flipping a coin, you can substitute it in. And so this is a kind of very basic random variable. It's called the binomials, one of the simplest. And we saw previously, and you should be able to justify now with some arguments about independence and counting, that if I look at my PMF, fx, which of course for a discrete random variable is the probability that my random variable ends up at little x, we had argued that this is n choose x. I choose which of the n, so this is, let me just say, this is the probability of getting exactly x out of n heads. Okay, so I don't know which of them, but x of them are going to be heads out of my total of n. So the probability there is n choose x, so I choose which of the n coins are going to come up as heads. And then independence says that the probability of getting that arrangement, I have probability p for x of them, and 1 minus p for n minus x of them. So that's the PMF, and we kind of justified that in a previous lecture. And so basically, I want x of them to come up heads, so that each of them has probability p of coming up heads, so I have p of the x, and I have probability 1 minus p of getting tails on the remaining n minus x of them. So I get 1 minus p to the n minus x. Okay. One thing I would have to justify, I'm not going to totally justify it, but I'm going to use this fact. We know that this PMF is a valid PMF, or in a claim it's a valid PMF. So if I sum this PMF, we have this condition that in order for it to be a valid PMF, if I sum the PMF over all values of my support, it gives me 1. And the values of my support in this case are, I can get 0 heads, 1 heads, 2 heads, 3 heads, all the way up to potentially n heads. So if I sum x goes 0 to n of f of x, I should get 1. Now, that's true, but it's not trivial to see that from the form of this PMF. I'll give you a hint, and it will also help explain the name. So there's something called the Binomial Theorem. And the Binomial Theorem says that if I look at x plus y to the n, I can expand this out in terms of binomial coefficients. So I can expand this out as a sum where I goes 1 to n in terms of binomial coefficients as such. Something along those lines. That's the binomial theorem. It says, which we all kind of know, is that I can expand out, if I take x plus y squared, you get x squared plus 2xy plus y squared, etc., right? You can keep playing that. If you do x plus y to the third, you get a bigger kind of polynomial, and you can play this game. And the general formula follows this rule. And this rule is called the binomial theorem. In our case, this binomial theorem can be used to show that this thing sums to 1. So I believe, I'll not totally do the proof, but I believe you can do something like this. Is like p plus 1 minus p to the n. that should give you, it should be something like that. Yeah, I think that's a good enough hint. But you can show, main point is you can show that this thing sums to 1. Okay, which is not super trivial. You have to believe this binomial theorem. Okay, not the main point. The main point here is we'd like to calculate the expected value of x. If x follows this distribution with this PMF given as follows, what is the expected value? So we're going to see a nice little trick to prove this. So the last one we saw was, okay, remember integration by parts. And this is another trick that's useful not only for discrete random variables, but will be useful generally. Now, I'll tell you when the trick comes about. So first of all, let's expand out our definition, right? So our definition of expected value is that for a discrete random variable, it's the sum of x times the PMF, and I sum it over my support. And in this case, or all values, but it's only non-zero for my support, right? So in this case, my support is 0 to n. And first off, I want to notice that when x is 0, if x is 0, then x by fx is 0. So I actually can ignore this, and I can change this to start at 1. So I can instead write this as the sum from 1 to n x fx. Okay? Let's expand out what fx is. This is sum x goes 1 to n of x, and fx is n choose x, p to the x, 1 minus p, the n minus x. As an aside, I want to look at this term, x, n choose x. So let's look at x times n choose x. Let's expand out what n choose x is. It's n factorial over x factorial, n minus x factorial. So I'm just going to expand out what that is. And x factorial is x by x minus 1 by x minus 2, etc., right? I could cancel my x on top with the 1x on the bottom, and I could change that to an x minus 1 factorial. That's allowed, because x factorial is x times x minus 1 factorial. So if I did that, I would say that this is n factorial over x minus 1 factorial, n minus x. The one last kind of trick I want to do is I'm going to factor out an n. So if I factor out an n, I would be left with an n minus 1 factorial on top. Let's actually move this all down so we don't crowd ourselves. All right, I would be left with an n minus 1 factorial on top. I factor out an n. I have an x minus 1 factorial on the bottom. And I can write n minus x as n minus 1 minus x minus 1. So these two things are equivalent. This thing, x times n choose x, and, well, let's figure out what this thing is. This last part is n minus 1 choose x minus 1. If you actually just write out, expand out what n minus 1 choose x minus 1. It's n minus 1 factorial over x minus 1, n minus 1 minus x minus 1 factorial. So I can play this game where these two things are equivalent. X times n choose x is the same thing as n times n minus 1 choose x minus 1. So this is a little bit of a trick, not the main one we're interested in, but it allows me to write this instead as n minus 1 choose x minus 1, and I still have my p to the x, 1 minus p to the n minus x. Okay. Now, what I want to do is I want to kind of change my variable here. I want to work with y, that's x plus 1, or equivalently, x is what, y minus 1? So if I substitute in, I could rewrite this sum instead of as a sum from x goes 1 to n. I could say it's a sum as y goes 0 to n minus 1. And everywhere I see an x, I can replace it with a y minus 1. So I have an n, I have an n minus 1, choose. Now instead of x minus 1, I should be able to write, I don't want x plus 1. Let's try this again. That's not the right transformation. What's the transformation I actually want, right? I want y to be x minus 1. There we go. Now it's a sum of y goes 0, right? When x is 1, y is 0. When x is n, y is n minus 1. N minus 1, choose. Now, correctly, we have y. P, now instead of p to the x is of course y plus 1, right? So we have p to the y plus 1, and we have 1 minus p to the n minus, what do we want? N minus y minus 1. Yeah, n minus x is n minus y plus 1. We can even write it like this if you want. N minus y plus 1. Same thing. Okay. So where are we going with this? Let's now factor out my n out of my sum. Let's factor out one of these p's. And what we're left with is the sum y goes 0 to n minus 1, n minus 1, choose y, p to the y, 1 minus p. Now what do we have? We can rewrite this as n minus 1 minus y. Okay. That does not look like, it looks like we're just screwing around, changing a bunch of variables. Let's just, as an aside here, let's define another random variable y. And let's say y has a binomial distribution. But instead of np, it's going to have a binomial distribution of n minus 1p. And so the PMF in this case would be, instead of n choose y, it would be n minus 1 to the y to the p, 1 minus p to the n minus 1 minus y, right? That would be my PMF, okay? If I plug in my binomial distribution. That is exactly what we have here. And what that means is that if I look at the sum over the whole support of y, 0 to n minus 1, that has to give me 1, right? Why is that true? Well, if we go back up, I made this whole big deal about the fact that this thing, that the sum of the PMF was 1. So this sum here, this whole sum here, let's write it like this, is the sum of PMF of a binomial n minus 1p. And that has to be 1. So that whole thing collapses down to 1, and what we're left with is just what we factored out, an n and a p. And that's done, that's complete. So what we get is that if x has a binomial distribution, our expectation is np. And that actually is a very interpretable expectation. If you remember what a binomial random variable is, you flip n coins, each of them have a probability p of coming up heads. How many do you expect to come up heads? Well, n coins, p probability, n times p. So our expected value is the number of flips times the probability of flipping of, let's say, probability of heads on any flip. That's, I think, very interpretable. As far as expected values go, it doesn't have to be that interpretable. But it is in this case of a binomial random variable. It's pretty much that's kind of, okay, yeah, if I have p percentage on one flip, then if I do n, I should have n times p. I expect to have n times p of them come up. The trick we saw here, a general trick, which solved this problem kind of in a complicated way, but you can, and we will again use it, is that often we can recognize in a calculation, if we're clever, you can recognize either the sum of a PMF or the integral of a PDF, say in this case over the whole real line. And you can recognize that these have to be 1, that the PDF has to integrate to 1 and the sum of the PMF has to be 1. So often we could recognize this, and it may take some work. So in the case above, we had to do a couple other little tricks in order to get it into the right form, where we then could recognize the sum, which looks like a horrible, nasty sum, and really would be, into something that's really straightforward and simple. Oh, that's just 1, right? And so the trick here is not just for this binomial random variable, and we'll see it again today. It is a general trick, is that often when you're doing these kind of calculations of expected value, you can, so the expected value would have an x in here, right? But oftentimes you can manipulate it so you get just either the sum of the PMF or the integral of the PDF. And if you can do that, then you can recognize, aha, that thing has to be 1. And therefore you make your problem a lot simpler. So that's kind of a general trick to file away. In fact, you can solve some of the ones that you would have to do with integration by parts. You can solve them with this trick, and we'll see that later too. Okay, so let's talk about functions of random variables, and specifically, so let's say functions of random variables. What I'm going to just say at this point, of course, is note a function, let's say g, applied to a random variable, let's say x, to form what we're going to denote as g of x. This thing is a random variable. It's a random variable. So I can look at functions of random variables. So for example, I could look at x squared. Let's say if x is the number of heads, I could look at x squared is the number of heads squared. Or log x is the log of number of heads, assuming that number of heads is not 0. So any function of a random variable is also a random variable. Let me write that again. Any function of a random variable is also a random variable. And you can justify that to yourself. We'll just do a real quick justification, right? A random variable is a function from the sample space to the real line. And so if I were to look at, say, a function, a real valued function, I could write g of x, right? I'm going to claim that's also a random variable, because what I actually mean is that that this g of x is actually g of x. So what really happens is that we go, x takes us from the sample space to R, and then g takes us from R to R again. So it's just functional composition. That is g of x. Okay. That doesn't strike your fancy. You can ignore it, but the point is, yeah, if I have a random variable, I can also look at any kind of real valued function of it. We write it kind of as, like x squared log of x. And that's kind of the standard notation. Generally, we're going to write it as g of x for some function g. So a natural question is, if I have a random variable, what is the expected value of a function of its random variable, a function of that random variable? So that brings us to theorem, probably the best named theorem in the course. This is the law of the unconscious statistician. Named so because you can apply it unthinkingly like an idiot statistician, like myself. So the law of the unconscious statistician says if we have some real valued function, g, and x is a random variable, then if I want to calculate, instead of calculating, say, the expected value of x, what if I want to calculate the expected value of g of x? The law of the unconscious statistician says this is pretty straightforward. And it has two cases, of course. If we have a discrete random variable or a continuous random variable. In the discrete case, normally what we'd do is we'd say it's the sum of x times f of x. But now instead of looking at the expected value of x, we're looking at the expected value of g of x. And we can just replace x with g of x. Or in the continuous case, instead of looking at the integral of x fx dx, we're now just going to look at the integral of gx fx dx. So it's a really nice, straightforward theorem because it says you can kind of do what you want. And I can just push the g into my sum or push the g into my integral. And everything works out nicely. So let's look at an example. And we'll use our what's called, maybe I should give this a name. So this, you might call this the PMF/PDF trick for solving this. We'll use this in this problem. Okay. Example. So again, I'm going to have x has an exponential distribution with some parameter lambda, right? So again, lambda is some positive parameter, and this means that my PDF is lambda e to the negative lambda x, as long as x is bigger than 0. Recall, from way back at the beginning of the lecture, expected value of x is 1 over lambda. And the other fact which we're going to use is, of course, that, how do I want to write this? If I integrate my PDF over the real line, that should give me 1. So the integral of lambda e to the negative lambda x dx is 1. Okay, what does this have to do with anything? Here's the question. Let's calculate, instead of the expected value of x, let's calculate the expected value of x squared. What we'll see, well, let's do the calculation, right? So here is that g of x in this case is basically like x squared. Okay, let's apply the law of the unconscious statistician, which says that the expected value of x squared is the integral. Instead of x, I put x squared fx dx. Okay. And let's expand out. Of course, we can just look at from 0 to infinity because the PDF is 0 if we have a negative value. And so this is x squared, and the PDF is lambda e to the negative lambda x dx. This looks like another integration by parts problem. So let's at least start the by parts problem. It's going to be simpler than the last time. We had luck last time. Let's say u is x squared, which means du is 2x dx. And that would mean that dv should be lambda e to the negative lambda x dx. And so, as we saw last time, that means this is negative e to the negative lambda x. Okay. In this case, I'm just going to continue this down here. This thing we can write as, so it's the integral of u dv, which of course is uv, minus the integral of v du. And uv is, well, x squared is a negative e to the negative lambda x minus e to the negative lambda x. Whoops, and du is what? 2x dx. Right? Okay. So let's add in some limits now. This is 0 to infinity, right? So this is evaluated 0 to infinity. And by the same argument as we had last time, this whole thing is going to be 0. So you can do the kind of limit at 0. 0 is clearly 0 times whatever, 0. And infinity, again, the exponential term dominates. The whole thing goes to 0. This leaves us with the following integral. I'm going to factor out that 2. And the integral is then x e to the negative lambda x dx. And in fact, what I'm going to do is I'm going to divide through by lambda here, and I'm gonna stick a lambda in here, right? That's allowable. I can multiply by 1. And what I'm going to notice, like the PDF or CDF trick, I guess we don't use the exact same trick. This is the expected value of x. Because this is the PDF. This x times PDF, you integrate. Of course, where there are limits 0 to infinity. That's the expected value of x. And we had already calculated what the expected value of x is. So what we get is we get 2 over lambda times what's the expected value of x? We said it was 1 over lambda. And all together, we get 2 over lambda squared. And so what we were calculating, you go back up top, was the expected value of the square. Notice, so first of all, we use this trick, which is kind of like the CDF or PDF trick, except we recognize the expected value. Notice that expected value of x squared is, what is it, 2 over lambda squared. That is not equal to 1 over lambda squared, which would be what we get if we were trying naively just factor out that square. So you can't, if I want to calculate the expected value of x squared, I can't just factor it out. I can't say, well, that's the expected value of x squared. That would give us 1 over lambda squared, not 2 over lambda squared. And that difference really matters. So unfortunately, you can't just pull that nice little trick. You have to calculate the whole thing. Okay, before we start talking about, well, we're going to start talking about properties of expected value. And in order to talk about the properties, I want a real quick aside here. We're going to do some more kind of Calc 2 review. So recall improper integrals. Okay? Improper integrals. For example, if I wanted to, I could integrate from 0 to infinity 1 over x squared dx. That's fine. We can actually, there is some answer for that. Even though at 0, technically this thing blows up, right? You can get an answer. So this has a finite answer. Like, in the same way, is if I summed, say k goes 0 to infinity, if I looked at my sum of 1 over k squared, if you remember in Calc 2, this thing was less than infinity. It converged. It converges. Has some finite value. However, if I looked at the integral like 1 over x dx from 0 to infinity, this doesn't converge in the normal way to a finite value. And this is kind of analogous to how if I were to look at my harmonic, I guess this sum starts at 1, doesn't it? If I look at my harmonic series, sum of 1 over k, that thing, let's say, is infinity. The better way to say it is that it doesn't converge. Okay? So sometimes integrals converge, sometimes they don't. And in particular, this one doesn't. Question. Does expected value always work? Does it always converge? Another way of saying this is, does expected value always exist? We've defined expected value in terms of sums, potentially infinite sums, and integrals. Those things don't have to have finite values. So another way of thinking about it, does it have a finite, well-behaved value? Of course, the answer is no, because we define these in terms of sums and integrals. And let's just look at one case where things don't work out, where the expected value doesn't actually exist. Typically in this course, we'll look at examples where expected value does exist, but it's possible, and you should know, that expected value doesn't need to exist. We're going to look at what's called a Koshi distribution. That name may be familiar if you take an analysis. Koshi. And the Koshi distribution is kind of like the normal distribution. You won't necessarily believe that from the form. The form of the Koshi distribution looks like this. 1 over pi times 1 over 1 plus x squared. And this is for all real numbers. If we were to plot the Koshi distribution at 0, well, first, if we were to plot a standard normal distribution, so this is my bad drawing of a standard normal, that's looks kind of bell-shaped. The Koshi distribution is also kind of bell-shaped, but it has fatter tails, as they say. So it's going to kind of be like that. So this is a Koshi distribution. It looks kind of like a normal, but it's not. It's kind of bell-shaped. One of the main problems is with this Koshi distribution, and it looks like a fine. You can actually show that this is a valid PDF. It's a valid random variable, but it doesn't have a finite expectation. So let's try and calculate the expected value of this Koshi random variable. Okay. It's going to be my integral, negative infinity to infinity, of x fx dx, which is this. Plug in what's going on in my PDF. So that's the integral I get. My argument is that the 1 over pi doesn't matter. This looks like asymptotically x over 1 plus x squared. Okay? And asymptotically, so it is x over 1 plus x squared. Asymptotically, it looks a lot like 1 over x, right? For x really, really, really large, that 1 isn't going to matter. It's going to look like x over x squared, which is like 1 over x. And so it's going to integrate like, so behaves like the integral of, let's say even this, negative infinity to infinity of 1 over x. And that doesn't converge. And so this Koshi random variable won't have, so no expected value. This random variable doesn't have an expected value. In the normal way, we can't assign it a number. In some ways, it's an okay distribution. The Koshi distribution is a very weird distribution. It's often used as counterpoints to theorems, for example. Surely that expectations always exist. Well, no. Koshi shows that that's not always true. Okay, so that's kind of a weird property. Let's talk about some nicer properties of expected value. Okay. Theorem. Properties of expectation. We're going to go through these kind of quick. Property 1 is that expectation is linear. What does that mean? It means that if I look at the expected value of a x plus b, I can write this as a times the expected value of x plus b. Actually not so hard to prove in the continuous case, so let's just do this for the continuous case. Of course, expected value is just integration, and the law of the unconscious statistician says if I want to look at the expected value of ax plus b, I integrate ax plus b against my PDF, and the rules of, let's say, integration is linear. I can pretty much just leave it at that. Integration is linear, and therefore expectation is linear. And in the discrete case, you'd say summation is linear, therefore expectation is linear, right? What I'm allowed to do is I could say this is a times the integral fx fx dx plus b times the integral of fx dx, and this thing is 1. So this is a, that is just ex plus b. So you can pause and think through that proof real quick, but I'm just distributing my fx across using the fact that expectation is linear, or I'm sorry, integration is linear. This thing, this last term here, integrates to 1. So everything's nice and simple. So expectation is linear basically because it's defined as summation and integration, and those are linear. Other nice properties, say property 2, is that if we have a random variable that is positive, say bigger than or equal to 0, then expected value of x correspondingly positive. What I mean here when I say x is bigger than or equal to 0, I mean that the support of x is non-negative. Kind of in the normal way. It has 0 probability of taking on, or 0 density of taking on anything negative. And if that's true, then yeah, the expected value is also going to be non-negative. And let's look at a real quick proof in the continuous case again. Expected value, since my support is positive, I can just look at the integral from 0 to infinity, x fx dx, and x from 0 to infinity is positive. Fx, we know, is always positive. And so basically this is the integral of a positive function is not negative. If I integrate something that's positive, it's going to give me a positive number. Cool. Well, that's a very useful property too. And the third property we're going to write is kind of a similar combination of the first two, which is that if g1 and g2 are functions, then two things hold. Let's say I, which is that expected value of g1 of x plus g2 of x is expected value of g1 of x plus expected value of g2 of x. And factorial 2, if g1 is less than or equal to g2, let's say if I plug in any little x, the functions are bounded in that way by each other, then the expectations are also bounded in a similar way. So these two parts are kind of unrelated, part 1 and part 2, but they're just kind of general facts. So they have a similar flavor as the previous. You can prove these by applying A, B, and the law of unconscious statistician. Those three things combined. And I won't do the proof. It's actually not so bad, but those three things will get you there to a proof. And the fourth and final kind of fact, which is kind of, again, a very similar flavor, is that if my random variable, kind of similar flavor to number 2 here, is that if my random variable is bounded between two numbers, then so is my expectation. And you can do this by applying part 2. I wanted to say A and B here. This should be 1 and 2. Applying part 2 twice. Basically, you can get that fact. But just kind of to review the facts, is basically the first two are kind of the most important ones, that, and you can derive the other ones subsequently, but the kind of important facts here are: 1, expectation is linear. Super important. And then a subsequently less important but important fact is that it kind of respects this ordering in some ways. If it's bigger than 0 or bounded between two numbers, then it respects it. It kind of respects those bounds. And you can derive other kind of subsequent facts. I've shown you 2 of them, but those are the 2 most important. Linear, and it kind of respects these bounds. Okay. So in the last part of the lecture today, I want to start talking about the concept of variance. So variance. The general idea with variance is that I have my mean mu here, and maybe I have some distribution that is very concentrated. So here I'm looking at basically my PDF. Maybe I have a PDF that's very concentrated around my mean. Alternatively, I could have the situation where my density is not very highly concentrated around my mean. we would call the one on the left here low variance case, and the one on the right here the high variance case. And variance basically is trying to capture how spread out the distribution is around the mean. Kind of how spread out is the distribution around the mean. And this is the mean tells you where the distribution is, and the variance kind of characterizes how spread out the thing is. So you talk about this all the time in an intro statistics course or other courses. These two things, mean and variance, center, location, spread is another word for variance. But now we can actually formally, just like we formally defined what a mean is for a random variable, we can find what is the variance. And the variance, just like the mean, is some property, some number that we can assign to each distribution. And variance is actually going to be calculated in terms of expected value. So the variance of a random variable x is defined as, so the notation I'm going to use is VAR of x for variance. And the variance of x is the expected value of the random variable minus its mean squared. So it is kind of interpreted as what's the expected squared deviation from the mean. Why don't we write that down? Expected squared deviation from the mean. Other ways you'll see this written is, this is totally equivalent, you see the expected value of x minus its expectation squared, right? These two things are equivalent. Mu is just our notation for expected value of x. The expected value of x is just a number. So I take my random variable, I subtract off a number, I square it, that's some function g, and then I calculate the variance with the expected value. And again, it's just a number. So anything kind of in the output of my expected value is always a number. So this looks kind of like a scarier way of writing it because we have like nested expected values, but it's not really. E of x is just a number. Some 5, 3, 2.7, right? Just a number. So it's x minus some number squared. Okay, and then you throw that in the expectation. So it kind of looks, I think, more friendly writing it this way because it's like x minus number squared, but it's, you'll see it written both ways. So this is very much a traditional way of calculating spread using variance. And this is super, super, super important concept in statistics and probability. I want to note one thing before we look at some examples of how to calculate variance. So note here that if I define a new random variable, let's call it y, and y is going to be x minus its mean. So it basically just recentered x. So the distribution of x normally is centered at mu. So this is, let's say, fx. And then I've done this transformation. I can look at the distribution of y. It basically recentered the thing at 0. By subtracting off the mean, I basically just shifted my distribution so that its mean is now at 0. That's actually something we can prove, right? What is the mean of y? We can say, well, let's calculate the expected value of y. That's the expected value of x minus mu. And I claimed in our previous list of properties that expectation is linear. So I can push expectation through like this. And of course, that is mu minus mu 0. So the reason that we don't just say, well, let's just look at how far on average the expected value that x is from the mean is that expected value is always 0. So we square it. So that's why we have this square up here. Because if you just look at kind of how far typically do you expect x to be from its mean, pretty much definitionally, it's on average 0. So instead we look at the squared deviation. That makes everything positive, and therefore we don't get a expectation that's 0. Okay. Let's close out today's lecture with some examples of expected variance, actually. And let's do one example, and then we can look at some properties of variance. So, example, I'm going to continue on with my random variable x that has an exponential distribution with a rate parameter lambda. And recall, so far, we had calculated that the expected value of x was 1 over lambda, and the variance of, and the expected value of x squared, get this right, is 2 over lambda squared. Okay. What's the variance? Let's calculate the variance of x. It's another property based on expectation. And so mu, which is the expected value, is 1 over lambda. By definition, variance is the expected value of x minus mu squared. And the law of the unconscious statistician says that I can write this as the integral of x minus mu squared times fx dx. And my integration limits are 0 to infinity because exponential random variables are positive random variables. So let's merrily go about here. Let's expand out my square. Make this really hard for ourselves. X squared plus 2x mu plus mu squared. I guess that should be a minus 2x mu, right? X squared minus 2x mu plus mu squared times fx dx. And then let's distribute my fx through. So let's say that's integral. Well, we can break this into a couple of integrals, right? So it's going to be integral of x squared fx dx minus 2 mu integral of x fx dx plus mu squared integral of fx dx. So that's just distributing through and using linearity properties of integration. And now we can again use our nice little trick. We can identify this is the expected value of x squared. This is the expected value of x. And this is the integral of the PDF, which is 1. So that uses all the little tricks we've had. And so what we get left with here, expected value of x squared, 2 over lambda squared, minus 2 mu, of course, is our expected value. So that is 1 over lambda, and expected value again is another 1 over lambda. And then we get plus mu squared, which is 1 over lambda squared times 1. So what we get, hopefully if I've done this correctly, 2 over lambda squared minus 2 over lambda squared, plus 1 over lambda, plus 1 over lambda squared. And at the end of the day, we get 1 over lambda squared. And that, I claim, and think I've just shown, is the variance. So for an exponential random variable, the variance is 1 over lambda squared. And we use some nice tricks. Actually not that bad of an integration problem because we already knew, because I had calculated this before, expected value of x squared and the expected value of x. So it's actually not so bad. And so what I see in this problem is all we needed to calculate the variance was we needed to know what the expected value of x squared was, and we needed to know what the expected value of x was. And this is generally true. it leads us to a really nice theorem. So let's write this theorem down. And this is called the shortcut formula for variance. And it works for all random variables. It says that if I want to calculate the variance of x, all I need to do is know the expected value of x squared, and then I subtract off the square of the expected value. So all I need to know is expected value of x squared and expected value of x. And what I do is I say the variance of x is the expected value of the square minus the square of the expected value. So memorize that. That's the mantra. Expected value squared minus the square of the expected value. Notice these two things will not be equal, and the variance generally won't be 0. So we pointed that out previously. You can't just distribute that square to the outside of the expected value. This is a really useful shortcut formula for calculating variance because it's often easier to calculate the expected value of x and expected value of x squared and then just combine them by this formula instead of going through the whole hog of calculating the definition of variance. In fact, I'd say that almost always it's quicker to use this formula. Hard pressed to think of a situation where it wouldn't be. So pretty much people see this theorem as synonymous with the definition, but it is not actually the definition, it's just the theorem. The proof of this is actually something we can do now because we can use our properties of expectation to prove this. So the variance we said was the expected value of x minus its mean squared. And let's just expand that out. That's the expected value of x squared minus 2 mu x plus mu squared. So the expected value of that whole thing, right? This looks a lot like the problem we just solved, because it is. So we just expand out that square. Expectation is linear. So we get expected value of x squared minus expectation is linear, so I can pull out constants like 2 and mu. And in fact, I can pull out the mu squared also, right? So this all comes from the linearity of expectation. And so what are we left with? We are left with expected value x squared minus 2, and let's just replace mu with expected value of x, because that's what mu is. So this becomes expected value of x squared plus expected value of x squared. And so what we get at the end of the day is what I claimed. Expected value of x minus the square of the expected value. Expected value square minus the square of the expected value. So let's say expect of square minus square of expectation. That's the formula. If we had known this formula, our previous problem would have been easier. So as above, let's just look at that same problem again. We could have just said, if we had known about this formula, that the variance is the expected value. So this is a problem where, again, I have my exponential distribution. If we had known this formula, we could have just applied it and said, it's the expected value of x squared minus the square of the expectation. And we had already calculated these two quantities. We had said this was 2 over lambda squared, and this was expected value is 1 over lambda, so we square that. And so we got 2 over lambda squared minus 1 over lambda squared, which leaves us with just 1 over lambda squared. And that is exactly what we got. If we scroll back up here, as our variance with a more complicated route. Okay. So the last thing I want to close with for today's lecture is just some properties, or at least one important property of variance. And this concerns, so for expectation, we saw that if I looked at the expected value of some linear function of my random variable, like ax plus b, that worked out real nice. So the question, I could just kind of distribute everything. The question is, what happens for variance? And it turns out it's nice, but not quite the same. I can pull out an a squared, and I can get rid of the b. So the variance of ax plus b is a squared the variance of x. So the kind of two takeaways is multiplying means I need to square the coefficient. So if I multiply by a, that means if I multiply x by a, my variance goes up like a squared. And if I add constants, there's no change to variance. Variance does not depend on constants. It's about spread around the mean, not where the distribution is located. So I can shift my distribution around. It doesn't change how kind of the spread of the distribution. It just changes where it's located. So variance of x plus b is the same thing as variance of x, and the variance of ax is a squared variance of x. All right, so that's kind of key takeaway here. So variance ignores additive shifts, and multiplicative constants get squared. The proof of this is not too bad, and I think it's worth going through here. Let's use our shortcut formula. So our variance of, what do we want? Ax plus b. The shortcut formula says that this is the expected value of the square minus the square of the expected value. Okay? And this is just a game of expanding things out at this point. So I'm just going to continue on down here. Expected value, let's expand out the square. A squared, that's where that comes from. X squared plus 2ax, let's say 2abx, plus b squared, right? And then this thing is a times the expected value of x by linearity plus b, but then that whole quantity is going to need to get squared. So continuing on to the next line, I can apply linearity. I can pull out constants. Right? Any constant can be pulled out of that expected value like that. And I get a b squared. And then I'm subtracting off. I just have to square this out. It's a squared, expected value of x squared. So you're kind of seeing where the parts are coming from here. Plus 2ab, expected value of x. Yep, and then we're just left with a b squared on the end, right? And I have this mighty useful minus sign here, which is going to cancel a whole lot of stuff. All that's going to be left here is an a squared times the expected value of x squared minus an a squared times the expected value of x quantity squared. And I can factor that out, and I'm just left with my shortcut formula. So this last step is just the shortcut formula. Applied a second time. So unfortunately, it's not quite as nice that you can just push all constants out of variance like you can with expectation. But it's not a bad formula. You actually can ignore additive shifts, which can be really, really useful. And the constants, the multiplicative constants, just come out as squares. So let's leave it for there. That's kind of a tour de force on expectation and variance.